Here is the analysis filter bank. Just the filtering can be written with the convolution equation given here. The filtering and subsequent downsampling by capital N of the kth analysis filter H subscript of N of impulse response length L can be written as a downsampled convolution sum with phase offset N subscript 0, simply with the substitution M times capital N plus N0 by N prime, and have the new argument M of Y. So we end up with this here. So you need to go back to lecture 1 to review this. Now M is again the downsample index at the lower sampling rate. N0 is our phase index for the downsampling. Often we assume N0 equals to 0, which means that we start downsampling at the first sample, keeping the first sample. In this way, the sum only computes values which the downsampler keeps. The downsampling in this equation is now the hurdle to simply applying the z-transform to turn the convolution into a multiplication for easy invertibility. To look for a solution for invertibility, perfect reconstruction and aliasing constellation, we now take a detour to fast implementation using transforms like the DFT and its fast implementation, the FFT. This is also the approach used by the short time Fourier transform, STFT. If we divide our signal into blocks of length capital M, so here we are dividing our signal into blocks of length capital N, where M is the block index or index at the lower sampling rate. You can imagine the signal as a long horizontal sequence of samples which we subdivide into small blocks of length capital M. We then stack those blocks on top of each other. Then, going vertically down, we obtain downsampled versions of our signal at different phase lags. We see here. The DFT computes a block with capital N frequency or subband values for each signal block X of M. If capital T is the DFT transform matrix, then the DFT of each signal block is given here, where Y of M contains the DFT coefficients, as we show here. Here, Yk of M is the kth DFT coefficient for block M. Hence, index K denotes the subband or frequency, and the index M is the block index or time at the lower sampling rate. Hence, if we keep K fixed, we obtain a time signal for the K's subband. If we keep M fixed, we obtain a spectrum for block M. This is very important. So once again, if we keep the K fixed, we obtain a time signal. If we keep M fixed, we obtain a spectrum. That is why this is called a time frequency representation, since we have both time M and frequency K indices in it. This shows that the DFT is simply a special case of an analysis filter bank with critical sample and perfect reconstruction through the inverse DFT.